Okay, hi everyone. Thank you for coming. My name is Timur Doumler. You will find me on Twitter under Timur_audio. I'm a developer advocate at JetBrains. We make developer tools such as the C-Line IDE. If you want to talk about that stuff, please come and find me later. This talk, just a disclaimer, it's a kind of shortened 60-minute version of a 90-minute talk that I did earlier this year at C++ Now. And it's about a kind of journey that I have embarked on earlier this year. And I'm still very much in the middle of that journey. So this is all very much work in progress. And I kind of want to talk about what I learned along the way as I embarked on this journey. Why do we talk about shared pointers in 2022? As multiple people already this week have mentioned, this is not good. It's shared global mutable state, right? This is not good. But first of all, well, you can have a shared pointer to const t, and that kind of makes the whole problem of global mutable state kind of evaporate, or shared mutable state. And then we're not actually going to talk too much about kind of the shared pointer aspect, but more the atomic shared pointer aspect. In particular, an atomic shared pointer is the thing that allows you to basically do this in a thread-safe way, where you can share data or an object and manage its lifetime across threads in a thread-safe way, right? Without using locks or mutexes. And there are use cases for this, quite a few interesting use cases. I'm not going to talk too much about the use cases. I'm going to mention just a few things. Hanna Dushikova gave a talk earlier this year about Lightning updates. So she was showing how to build a system where you have an app and you have different parts of the app basically updating the state. And you kind of have to share those objects across the program. And this is just a snippet of code from her talk where she was using atomic shared pointer to achieve that. And it kind of makes it relatively simple and elegant. And here's another screenshot from a talk I gave here in 2015, which was actually my first conference talk ever. And there I was talking about a similar use case where you share kind of objects across threads, and they kind of pop up and they need to be destroyed, but you need to make sure that they're not destroyed while another thread is accessing it. Everything has to be thread safe. But this was also about audio software, where you have one thread which is a kind of processing thread which runs under real-time constraints. So you cannot take a lock there. You need to program in a lock-free way. And now we're talking about a lock-free atomic shared pointer to solve this problem. And if you go back to this was kind of about single objects that kind of pop up in one thread. You need to like share them with another thread and then make sure that they're destroyed at the right time. But sometimes you also need to do this with a whole range or set of objects or a stream of objects or something like this. And then you're talking about lock-free data structures. And again, that's a huge topic, which I'm not going to cover today. There are good talks about this. Here's one. Further, he was talking mostly about read, copy, update in that talk, but he also had this comparison table. Three kind of mechanisms or elemental building blocks that you can use to build lock-free data structures. And so he was talking about RCU, hazard pointers, and the atomic shared pointer. And if you have a lock-free atomic shared pointer, you can use that as a building block for lock-free data structures. And these three mechanisms, they're all being used in different scenarios. They all have different trade-offs, so it kind of depends on the use case and the data structure, which one you're going to end up using. But the atomic shared pointer has its place, and therefore Herb Sutter actually in 2014 wrote a paper to add it to the standard. And here he mentions as the motivation for the atomic shared pointer ABA and robustness and efficiency. And what is this about? If you look at, for example, a lock-free queue, there's implementations of multi-producer, multi-consumer lock-free queues. Open source, for example, there is Boost lock-free. There is Moody Camel queue. And if you look at those implementations, they're usually horrendously complex. You have each like load and store operation. There's like a huge big CAS loop with like multiple atomic operations inside and like many special cases. And it's all really, really complex and almost impossible to reason about and very, very hard to come up with these structures. But it turns out that most of this complexity comes from basically two things you need to do if you have a log-free data structure. One is you need to share the lifetime of your elements in the queue, right? So you need to make sure that they're not being destroyed while another thread is still reading them, for example. And the other thing is the ABA problem, right? So this is something that I'm not going to go into, but it's something that is a problem with log-free data structures, where kind of one thread removes an object and then puts another object in the same place, and then the other thread can't tell that the object actually has changed, and then kind of everything explodes. And it's extremely hard to get around this problem. But the interesting thing is that the atomic shared pointer kind of very neatly encapsulates both of those things. So the atomic shared pointer obviously handles the lifetime aspect, because that's literally what shared pointer is for. But also, it handles the ABA problem, because the shared pointer it doesn't work with indices or something like this. It knows about the identity of the object that it's managing. And therefore, you will not run into an ABA problem if you build your log-free data structure on top of a log-free atomic shared pointer. And here's actually an example from Herb's paper where he implemented a concurrent stack, and you can also do a concurrent queue. It's not going to be much more complicated than this. And this is a correct implementation, or like a lot of people have looked at this, and I'm pretty convinced that it's correct. Implementation of a log-free stack where you have push front, pop front, and you also have a find operation. And you can do all of these things concurrently from as many threads as you want. And the whole thing still fits on one slide. This is like the complete implementation. And the secret here is the atomic shared pointer, and that encapsulates kind of all the nastiness. And that's why it's kind of very good to have as a building block for kind of these use cases. So log-free atomic shared pointer, obviously the first aspect of this is the shared pointer aspect. So we have shared pointer, atomic, log-free. We kind of need to talk about all of this. Shared pointer, hopefully everybody here knows what a shared pointer is. I'm just going to very, very quickly go over this. So the standard says that a shared pointer is a smart pointer that manages an object usually obtained via new, so it's on the heap. It implements semantics of ownership, and the last remaining owner of the pointer is responsible for destroying the object, and that's typically achieved with reference counting. So this is a very, very simple diagram of how a simple shared pointer is implemented. The shared pointer itself holds a pointer to something that is a control block. We call it a control block. And the control block has a pointer to the actual object that's being managed. It has a reference count. And then it has the object itself. And depending on whether or not you allocated the shared pointer with std make shared, the object might be in the same block of memory as the rest, or it might be in a separate block. And then what you can do is you can, for example, copy the shared pointer, and then you're going to have a second shared pointer pointing to the same control block. And when you create the second shared pointer, you're going to increment the ref count. Okay? So now the ref count, which is in the control block, is 2 because you have 2 shared pointers pointing to it. If then the second shared pointer gets destroyed, the ref count goes back to 1. And then if this instance of shared pointer is destroyed, then the ref count goes back to 0. And as soon as that happens, the object that's being managed is deallocated. And then the control block itself is also deallocated. And depending on whether you use make shared, that might be 1 deallocation or 2. Okay, so this is kind of a very quick explanation of what a shared pointer does. Now, what is an atomic shared pointer? So atomic in itself just means kind of indivisible. That's kind of what the Greek word means. It means it's basically thread safe. If you're using an atomic object, it means that you're not going to have data races, and you don't need to use locks, right? This is a very simple explanation of what atomic means. So it's about thread safety, essentially. And should we look maybe at whether or not a shared pointer is actually thread safe? So the standard doesn't say very much about this. The standard only says that changes in use count, which is the same as ref count, do not reflect modifications that can introduce data races. So this is the only thing the standard says about whether or not a shared pointer is thread safe. So what does that mean? It means changes in ref count are when we add or remove some of these shared pointer instances that point to the same control block, right? So when we say this is thread safe, it means that we can copy this shared pointer on one thread, and we can take another copy on another thread concurrently. And now we have 3 copies, and even though the copies happen on different threads, the ref count now is going to be 3, and all threads are going to agree on that the ref count in the end is 3. And that's typically achieved by making the ref count an atomic counter, right? So hopefully that's not surprising. So as we saw, if we have a shared pointer here, the putter is just a shared pointer, and we take a copy on one thread and we take another copy on another thread, this is fine, right? This is obviously thread safe. But what happens if we flip the last one around and we make it into an assignment? So now on thread 1, we're copying the shared pointer, and on thread 2, we're assigning a different shared pointer to it. Is this thread safe? Okay, you're right. This is undefined behavior. This is a data race. Okay, you cannot do this. And I think when I first saw this, I was kind of a little bit surprised because I was like, wait, is it like half thread safe? Like, this is a bit weird. But then I realized that it's actually not surprising at all. It's exactly like an int, right? If you have an int, you can copy an int on 2 different threads at the same time. But if you copy an int on one thread and assign to the int on another thread, that's a race condition, right? So the shared pointer in this case behaves just like any other C++ object. So there's nothing surprising here. We have had a way to get around this problem since C++ 11, since shared pointer itself is in the standard. We had these freestanding functions. They look a little bit weird. They're these freestanding functions that are called atomic underscore something, and then you write like the atomic operation you want to do, so atomic underscore store or load or whatever, and then you give it a pointer to the shared pointer as the first argument. So it's like this weird API which looks more like a C API, right? So we have there all of the atomic operations on a shared pointer implemented like this since C++ 11. And with this, we can make this code thread safe by not doing any copies or assignments just with the shared pointer, but always doing it through these freestanding functions, right? So whenever we want to read from a shared pointer, we need to write std atomic load, and whenever we want to write, we need to write std atomic store and pass this pointer the address of the shared pointer, which is kind of really weird API, as the first argument. And this has been in the standard since C++ 11. Unfortunately, this is not a great solution for several reasons. One of those reasons is that it's impossible to implement this efficiently. Like, let's forget about the log-free aspect for a minute, and like kind of the naive implementation of this would be you have a lock that guards the shared pointer, right? So, and if you have an atomic shared pointer class, you can put that lock right next to the shared pointer, right? You can encapsulate that in an object. But if you have a freestanding function which needs to be able to work with any shared pointer, you can't do that. So you only have bad options. You can either have some kind of global table where for every shared pointer you have like a mutex and you need to do this lookup, or you can just have a global mutex for all the shared pointers in the world, which is apparently how some implementations actually implement this. So you can't implement this efficiently, but then the much bigger problem actually is that it's unsafe by default, right? So if you have a shared pointer and you want to do atomic operations on it, then you have to remember to use these freestanding wrapper functions, right? And you have to remember to not access the shared pointer directly ever, because as soon as you do that, even in one place in one thread, your whole program is undefined behavior because you have a data race, right? So you need to remember to use these weird functions instead. So the default is the data race, and you have to actively do this weird thing to not have a data race. So it's not a great solution, and that's why Herb wrote this paper in 2014 proposing an atomic shared pointer as a type. And in C++ 20, we now got it. So we have atomic shared pointer as a specialization of atomic, std atomic in the standard since C++ 20. And with that, we can solve the problem much more elegantly. We can now create an atomic shared pointer. And now we can just use .load and .store. It has the same API as every other std atomic. And you don't even have to write the load and store. You can just write a normal assignment or a normal kind of copy. And it's going to be equivalent to the load and store operations. So it's kind of a matter of code style. I do actually personally like to write .load and .store, so it's obvious that it's an atomic operation. But some people might prefer to do it like this. This is a matter of code style. So basically, we have solved that problem. And now we can look at the next thing, which is the log freeness, which is something that you want to do if you work in any kind of real-time or low-latency environment, such as, for example, in my case, it was audio processing. There are lots of other use cases where you need to work under tight time constraints, and you cannot take a mutex because you don't have no idea how long it's going to take for you to acquire the mutex, and also you have the problem of priority inversion, so you cannot work with mutexes, you need a log-free implementation. And so, in C++20, we have atomic share pointer, and it's actually already implemented in MSVC and GCC, and I don't know how the Clang implementation is going along, but we have these two implementations, and when I knew that it's going to come in the standard, I was like, well, surely we're going to get log-free implementations, right? Because otherwise, it's not useful for me. Unfortunately not. So I went on Twitter. That was before the C++20 standard came out. And I was like, hey, so we now voted this into the standard. So surely your implementation is going to be log-free, right? And then SDL, the maintainer of the Microsoft standard library, told me, well, no, and also I'm not sure it even can be implemented in a log-free way. Like, how would you even do that? I don't think that's possible. And I was like, yeah, this is bad news. And yeah, it turns out if you use the standard versions today on the two compilers that do ship it already, GCC and MSVC, you get this. You have the log-free check in the std atomic. And if you do that, like every implementation reports that it's not log-free. So they're all implemented with mutexes inside. I don't know if they just wrapped the freestanding function version or if they actually did something more clever than this, hopefully. But in any case, these implementations have logs inside. So they are not usable for example, audio code or other other use cases where you have a tight deadline, you need to work with low latency and real-time constraints. And but then I thought, this is super weird, because on the one hand, I have all these standard library implementers, very, very intelligent people telling me, we are not going to implement this. We think it's not implementable. And then on the other hand, I have people like Förder, who is actually here this week, giving these talks where he's like, oh, yeah, atomic shared pointer, log-free. This is one of the things that you kind of use in this scenario. And yeah, I have an implementation of that lying around, no problem. And then there's somebody else, Anthony Williams. I'm sure many of you know him. He wrote the book about concurrency, C++ concurrency in action. So he's a very, very well-respected concurrency expert. And he has this library called Just Thread. And he wrote this blog post where he said, oh, yeah, so atomic check pointer, yeah, you kind of have the choice if you want to implement it log-free or not log-free. Log-free is obviously more complex. But you have these use cases where you need a log-free implementation, so I'm just going to add one. So he's like, yeah, I have an implementation too. Obviously, neither of them had their implementation available as open source. So now I had, on the one hand, experts telling me that it's not implementable, and on the other hand, experts telling me, oh, we have implementations and we use them, but they don't show me the code. And, and then I was like, okay, so either it's not implementable or it is. Both of those things can't be true at the same time. So that's when I embarked on this journey, and I said, okay, I need to figure this out. A, is this possible? And B, how do these people do it, right? And so I went and started kind of my research on this topic, and as I already said, MSVC and GCC have locking implementations. But then I actually found 3 open source implementations, and that was kind of earlier this year. I'm not aware of any new ones having popped up since then, but if there are, let me know. So I found these 3 which are available on GitHub today, and they're free and open source. And there's also at least one company I know of that has a closed source implementation, and then there's also Further, who has his implementation, but then later he told me his is actually intrusive, so it's different. It's not like the way it's implemented in the standard. It's like an intrusive implementation that's kind of tuned for the data structure, particular data structure that he has, so it's something a little bit different. What I'm talking about is kind of the generic version as it is in the standard. So there is at least these 3 open source and probably a few somewhere hidden in closed source projects as well. There is a hand here. Oh, sorry. The question was, what does intrusive mean? Intrusive means that the object that the class T needs to know that it's going to be used with a shared pointer. You need to add some provisions to the actual data class itself. So you can't use it with the generic, with any data. You can't have a shared pointer to whatever. You have to shared pointer to something that's aware of the shared pointer. It's basically a different type. It's not a generic shared pointer. It's something else which I'm not going to talk about today. So you can look it up, intrusive pointers. That's like a whole thing, which I'm not going to talk about. I'm talking about the generic. You can have shared pointer to a T, and the T doesn't know anything about shared pointers. That's what I'm talking about here, which is the non-intrusive version, the generic one. And so there are these 3. And there's also so Anthony's, this is not the commercial implementation that he has in his closed source library. This is like a kind of proof of concept version that he at some point published on his GitHub. So it's not like production ready. It's kind of just proves the algorithm. Then there is Folly, which is the Facebook C++ library. They have an implementation, which is the only one that I know of that is actually used in production. And then there's the third one by somebody called Vladislav Tulbashev. And he basically looked at Anthony Williams' implementation and said, I don't like this. It's not efficient. And then he looked at Folly's implementation and said, I don't understand how this works. So he went and implemented his own. And he has a blog post about this, which is brilliant. Unfortunately, it's in Russian, so I can read it because I speak Russian, but you probably can't, so maybe Google Translate can help you out. But yeah, it's kind of very interesting blog post. So there are obviously people who implemented this. So let's look at how we would do it, right? How would we implement a lock-free atomic shared pointer? So the underlying problem is that if you're kind of, imagine again this case where you have an atomic shared pointer and you want to copy from it on one thread and assigning to it on another thread, right? So if you're doing the assignment, you're modifying basically 2 things, right? You're modifying the control block pointer, because now your shared pointer is going to point to something else if you assign to it. And you're modifying the ref count, right? Because you need to, if the old pointer is going to get overwritten, you need to decrement the ref count. So you have these 2 separate values here, which you need to modify in one atomic operation, right? At the same time, in one atomic operation without a mutex. This is something that's called double compare and swap. So doing an atomic compare and swap on 2 separate memory locations at the same time. And it turns out there's exactly one processor that supports this, which is the good old Motorola 68000. So that processor has a double compare and swap instruction. So if you want to implement a lock-free atomic shared pointer on this particular CPU, that's going to be very easy. However, if you want to implement it on any modern architecture, it's not going to have that instruction. So it is simply impossible to do this. There is no instruction on any modern CPU to atomically swap 2 separate memory locations at the same time, 2 separate pieces of data in 2 separate memory locations atomically at the same time. That's just not a thing. And this is kind of what STL was referring to, like, if that's a thing, how can we possibly ever do this? Well, turns out we kind of can, because we have something else which is called double width compare and swap. And that is an operation that you do have on every modern CPU, at least Intel and ARM. Maybe there's some embedded architectures where you don't have that kind of stuff, but I'm not an embedded expert, so I don't know. I'm talking about kind of laptops, phones, that kind of stuff. So you have ARM and Intel, and they have this double boot compare and swap operation. The problem is the control block pointer and the ref count, they're not. So what this does is it can swap basically 2 words at the same time, but they have to be next to each other in memory, and they have to be aligned properly as well. So we cannot do this here because the control block pointer is in the shared pointer instance and the ref count is in the control block, so they are separate. Like there's no way for us to have them next to each other. So again, turns out, I mean, it looks like we're kind of stuck, but there is a really, really clever algorithm that gets us out of this conundrum, and it's called a split ref count. And I've never heard about this before. This is not something that you'd find in a computer science textbook normally. And David Goldblatt, who is the maintainer of the Forley implementation, told me, yeah, it's sort of a folk algorithm. There's like a handful of people who know how to do this, and it's kind of being passed from one to the other, like that kind of thing. Which is not great. I actually found 2 references to split ref count in the literature. There is one blog post by Dmitry Vyukov, which mentions split ref count, and there is actually also a mention of the split ref count idea in Anthony Williams's Concurrency in Action book. So it is being mentioned there. However, it's not being mentioned in the context of implementing an atomic shared pointer. So it's kind of the same idea, but it's a different use case, so it's not directly applicable. But like the idea does exist out there. You find it in the literature. It's just not, there's just not much material on it. So we kind of need to dive in and figure out how to do this, because there's nothing out there that is going to tell us. So we need to go into the implementations and talk to these people and figure it out. And at this point, I need to thank Anthony Williams, Vladislav Tsurbashev, and David Goldblatt, because I got in touch with all 3 of them and said, hey, can you please explain to me what's going on? And all 3 of them were very, very helpful. They wrote me long emails explaining stuff. I learned a lot from them. So this is one of the things I really like about the C++ community. You can reach out to people who know things that you don't, and they're usually super helpful, and you can learn from them. So that's great. So I'm just going to very, very briefly summarize how this works. What we're going to do is, instead of having 1 ref count, we now have 2 ref counts. We have a local ref count that lives in the shared pointer instance, and we have a global ref count which lives in the control block. And now what we can do is we can atomically modify both the control block pointer and the local ref count at the same time. And what you want to do is you want to modify the global ref count, but we can't do that immediately. So what we can do is we can increment the local ref count first, and then increment the global ref count, and then decrement the local ref count again. And then in the end, what we did is we just incremented the global ref count. But we can do it in this 3-step procedure, and in this way we can put a cast loop around it, and we can basically make sure that while we do this, nobody else has touched the local ref count or the global ref count. And if somebody else, another thread came in and modified them, we can roll back, we can have a cast loop around it. So just kind of very, very quick summary of this idea. So we have our atomic shared pointer, and what we're going to do now is we have this counted pointer structure in there, which is this control block pointer and the local ref count, right? And then we have now an atomic data member instance of the struct. And because it's atomic, now we can basically, by modifying this atomic, we can change both of those things simultaneously. And we need to check that it's always lock-free. More about that later. Let's, for now, just assume that this is going to compile. And as I said, this is kind of the basic idea. So if you want to increment the ref count, you will first increment the local one. We remember what state we're in. And then we are trying to sync them by doing this, right? And we can do that in a cast loop, so we can make sure that no other thread does that while we do the same thing, and then we end up in some weird broken state. So we are trying to atomically increment the global ref count and decrement the local ref count. But if another thread modified the state in the meantime, we basically roll back and try the whole thing again. But at some point, if we do succeed, then it means that the thread doing the operation, got to be the thread who did this ref count increase. So we're done, and we can we have a new state of the shared pointer, which we can return and we can carry on. And this is kind of something that you have to do pretty much for every atomic operation on the shared pointer. So I'm just going to show you the load quickly. So there's load, store, exchange, and compare exchange. And load is just the simplest one, so I can just about fit this on a slide. I could explain the others, but then the whole talk would just be staring at a wall of code, and I don't want to do that to you. This is maybe another talk, part 2 or something that I will maybe do another time, where we can go through the implementation, which I'm not going to do today. I'm just going to very quickly go through this. So here's kind of the idea. Here's how we could implement the load. So first, we load. So what you want to do is you want to modify the control block pointer, and then sorry, no, this is the load. So what you want to do is you want to take a copy of the shared pointer. So the only thing we really want to do is you want to increment the ref count and return the current state. That's all it is, right? So in order to just do that, increment the ref count and return the current state, we need to do all of this. So we need to load the current control block pointer, remember it, because we need to check later that no other thread has modified it, no other thread has assigned into the shared pointer. And now we have to increment the local ref count. And so annoyingly, we have to do this in a cast loop because it's this double word, right? It's this struct counted pointer, atomic counted pointer thingy, so we can't increment the whole thing. So we need to increment the local ref count in there. So we can't modify the whole thing atomically. Sorry, we can modify the whole thing atomically, but we cannot just increment the ref count atomically. So we need to increment the ref count and then do a compare exchange to make sure that nobody has modified the control block pointer while we incremented the thing. So this is just the increment of the local ref count. And then this is our new state, so we can remember that. We're going to return that later. And now we can increment the global ref count, just an atomic fetch add. And now we decrement the local ref count, and we do that in a cast loop, right? So we say, let's try to decrement the local ref count, and then do compare exchange. And if any other thread has, in the meantime, changed the control block pointer, or if any other thread in the meantime, if any other thread in the meantime has changed the control block pointer, then we were not the thread who was supposed to increment the global ref count, so we need to decrement it again and try again. And so we're going to be looping in there, and then eventually the compare exchange will succeed, and then it means, yes, we got to increment the ref count, and no other thread got in the way, so we're done, and we can just return the new state. That's just the atomic shared pointer load. So hopefully I convinced you that it is implementable, right? So we're not going to go through all the other operations, but hopefully this is enough to show you that you can implement this. This is a lock-free atomic shared pointer load. It's quite a lot of stuff, even like the simplest possible operation of the operations that you need. It has at least 3 atomic operations in there, and if there's contention, you're going to have more because you're going to be looping in this cast loop. So on its own, it's obviously going to be much slower than a mutex. Because if you acquire a mutex, if nobody holds this mutex, that's a very efficient operation. But even in the simplest case, if there's no other threads, you still have to do 3 atomic operations for the lock-free version. So it's definitely going to be slower. However, if there is contention, it's going to be much better because it's lock-free, right? You have the guarantee that if you are in this cast loop and you fail, some other thread has succeeded. So the whole system is going to make progress. Whereas if you wait on a mutex, you don't really have any guarantees whatsoever when the thread scheduler decides to call you. This idea, this is exactly how both Antony's and Vladislav's implementation works. Folly adds another kind of little tweak to that called ref count batching, which I don't want to talk too much about. Basically what they do is instead of incrementing the kind of global and local ref count kind of in steps of 1 every time, they kind of batch increment the global and the local ref count to some number k, which is bigger than the number of threads that you have. And then each thread is going to just eat off kind of these pre-incremented pre-incremented ref counts. So then you don't need to go to the control block anymore. You can just decrement kind of the pre-incremented version. And that saves you a lot of atomic operations because you don't have to touch the control block until you run out of these pre-increments. And then when you run out, you need to go to the control block to get more. And there is you can do this in different ways. So you can, like, when you go to the control block to get more, when do you do this? For example, when you reach half, or maybe you have many threads and you don't want all of them to go to the control block at the same time when they run out of increments. So you have some kind of like smooth function in there. So there's like lots of opportunity to tweak this. Very interesting, not gonna talk about it. The problem with this is that, or the trade-off is, if you do this kind of stuff, the ref count itself becomes meaningless, right? So the use count member function is not gonna return the actual ref count, it's gonna return some big number that doesn't mean anything. Which maybe it's fine, maybe you don't need use count. But this is kind of very typical for this kind of stuff, where the more optimizations you introduce, the more of the kind of generic like interface you lose, right? And the extreme case of that is kind of the intrusive version, where it's now very specific and it's not anymore like the generic shared pointer at all. So it's always like a scale of, do you want to implement the super generic version as it is in the standard with everything that it has? You can do that, or maybe we're gonna talk about that later, but you're not gonna get like the most optimized, fastest implementation probably. And then the more optimizations you introduce, the more kind of genericity in the API you lose. So that's kind of an example of this typical trade-off. So it looks like we're done, we can do this, right? Well, there is a problem. This is actually not how shared pointer works. This is a very, very oversimplified shared pointer. Std shared pointer actually has quite a lot more going on. Std shared pointer has a weak count because it also supports the weak pointer, right? Shared pointer supports a deleter, custom deleter, and shared pointer also supports a custom allocator. Now, none of this is really a big problem because they all live in the control block. We only have one of these. We only need to deal with the pointer to it, so that's not a problem. However, the big problem is that a shared pointer also has a pointer to the object itself. So the shared pointer has a pointer to the object, and the control block also has a pointer to the object. And that is necessary because they might not be the same. Shared pointer has a thing called aliasing constructor. Who's familiar with that here? Yeah, okay, quite a few people. So basically the idea is that the shared pointer manages the lifetime of one object, but it's actually pointing to another object. And ideally, if you don't want to have a bug, this other object should have the same lifetime as the first object. So you're going to be pointing typically to a member of that object that you're managing, or maybe to a base class or something like this. And so, this particular case is probably rare. It occasionally comes up in real code, but it's not a very common use case. But this is a much, much more common use case, right? So you have shared pointer to base, and you give it an object to derived. And because we have virtual functions and multiple inheritance and all of that stuff, pointer to base and a pointer to derived, they're not going to have the same address, even if they're pointing to the same object, right? So we need to deal with this, and now we have a problem, because now we have another pointer in the instance of the shared pointer, and now instead of modifying the local ref count and the control block pointer simultaneously, which we showed how to do, we now also have this pointer to the object it's pointing to, and we have to modify all three simultaneously, atomically. And you obviously can't do that. There is no triple width compare and swap. So it seems like we're stuck again. Well, so people found solutions. So Anthony Williams has a very clever thing where he says, okay, well, instead of storing the pointer, we're storing an index into another data structure, which is this weird kind of linked list thing. And that is an auxiliary data structure which only supports pushback, so it can only ever grow. And then you can do a lookup on it. And that's so simple that you can implement this in 30 lines of code, log-free. And so he uses this auxiliary data structure to store the alias pointers in there if you have a shared pointer with if you have multiple aliases pointing to the same thing. And then in the shared pointer, you have the control block, and then you basically cram the local ref count and the index into this data structure into one integer, which is fine because you don't need the full width of one word to store the ref count. You're hopefully not going to have 4 billion threads, and you hopefully don't have 4 billion integers for the alias pointers either if you're on a 64-bit system. If you're on a 32-bit system. And hang on. this is for 64-bit. So now I'm cramming the local ref count in the alias into 32-bit integers, and that's obviously enough. And so then basically we have 3 slots for the alias pointers pre-allocated. They just live in the shared pointer. And then if you have more than 3 aliases, we keep doing this pushback, and it works a little bit like a linked list in blocks of 3. It's very clever. However, it has a problem. These things are memory allocations, and memory allocation is not lock-free. So we can't do this. It's not lock-free if you have an alias shared pointer. And Anthony actually admitted that. We had a conversation on Twitter about this where a bunch of people chimed in, and Anthony said, oh yes, so this works if you have a lock-free allocator. And okay, well, if you're like, I don't know, Google or Facebook, and you have like a massive server where you like control the world, and obviously you have your own allocator, everything's great, you can do this stuff. But if you're on some kind of constrained system, I don't know, you want to write a audio synthesizer that runs on a phone or something, you probably can't do this kind of stuff. You might also not be able, you might not be in control of like all the allocations in your program. So if you need to allocate dynamic memory, it's not lock-free in general, so we're kind of stuck here. However, there is something you can do. So one thing you can do is you can move the allocation from the atomic shared pointer when you do the load or the store. Oh, and I should say this, if you have an alias constructor, like this allocation comes up everywhere. It comes up in the store, it comes up in the exchange, it comes up in the compare exchange. So like all of these operations are actually not lock-free as soon as you have an alias pointer, which is common if you have pointer to base and it's actually a derived. So what we can do though is we can move this allocation to the shared pointer itself. So we can say if you're creating an alias shared pointer, like at the moment where you create the shared pointer itself, that's when it's going to allocate additional memory to hold this alias structure. But then if you do atomic operations on it, you already have that, right? So that makes the atomic operations lock-free. However, that's overhead for every alias shared pointer, right? So even if you use a shared pointer without the atomic stuff, you're going to pay for that. Well, there is maybe another thing we can do, and this is something that I kind of came up with. Note that if you have an alias pointer, typically you're pointing to either a base class or a member inside that object. So hopefully those 2 memory addresses, they're not going to be super far apart, right? They're going to be relatively close. So what we can do is we can compute the pointer difference of these 2 addresses, and that's probably going to be small. And that pointer difference, we can then store that in a 32-bit integer. Hopefully your object is not big 4 gigabytes. Otherwise, you have a problem. So we can just compute the pointer difference between the pointer and the real pointer, like the object pointer, and store that, and we can cram that together with the local ref count into one integer. Or if for some weird reason the pointers are 4 gigabytes, more than 4 gigabytes apart, then we can do this extension list, which is the name of this auxiliary data structure. But it's such a weird use case, it's probably not going to happen in practice, and even if it does, we can still do the allocation in the shared pointer and not in the atomic shared pointer. So you still have, in every case, it's still lock-free. You just have this overhead and this one weird edge case, and we just can add 1 bit flag to indicate which method we're using, and we can put that bit into like an alignment bit, right? So that's fine. So have we now implemented a lock-free atomic shared pointer? Are we done? Well, there is one more problem. It relies on double width compare and swap. And then again, I ran into this thing where different experts were telling me different things. I had like lots of kind of CPU people telling me, oh yeah, double width compare and swap, like every modern Intel CPU, ARM CPU supports this, no problem. Every machine has this, like you can rely on this being there. And then I had C++ people who were saying, W compare and swap, oh no. In general, you don't have that. You have that sometimes, but like you can't really rely on that being there. Like you can't program with it. And I was like, huh, those 2 things can't be true at the same time. Who's right? And then I did a deep dive into this kind of subtopic of the whole problem, and I wrote a long blog post about this, this would be a whole talk in itself. So I'm going to just very, very briefly summarize it, but you can find it on my blog, timur.audio. Basically, the executive summary is, yes, double compare and swap is supported on every modern kind of desktop mobile CPU. So Intel has this compare exchange 8B and 16B instructions on 32-bit and 64-bit. There are some very old x64 chips that don't have that instruction, like basically AMD chips from 2008 and before. But basically, since then, every x64 CPU does have this instruction, and actually Windows requires it to run since Windows 8.1. So if you're running Windows, you know it's there. If you're running macOS, you know it's there. Only on some, if you're running Linux and you have like one of these really old chips, it might not be there. And then on ARM, my clicker is doing weird stuff. Yes, so on ARM, you have, on I think the latest ones, you also have like one instruction. On some other ARM architectures, you have this other thing, which is LLSC, load lock store conditional, which is a different way of doing the same thing, but it's effectively the same operation. So it's there, your CPU supports it. People were saying, yeah, but it's super slow, and I measured it, and actually, nah, it's not. On Intel, it's about twice as slow as normal compare and swap, which is unsurprising because it does double the work, so that makes sense. I tested it actually on the oldest machine I had around was a Mac Mini from 2012, and I measured it there, and even there it was 2 times slower and not times slower or something like this. So we don't have any kind of abysmal performance problem here. And then on ARM, it was even better. It was just 1.5 times slower on average. But the big problem is, does double-bit compare and swap work with stood atomic? So we know our CPU supports it, but does the standard library support it? In other words, is this static assert going to succeed, or is it going to fail? So this was me earlier this year. Our CPU supports it, and surely if we instantiate a stood atomic, which is double width, surely that's going to work, and it's going to just, your compiler is going to emit that instruction, right? Because it's there, right? So the compiler is going to emit that instruction, right? Wrong. And again, you can read my blog post, like it's a bit of a long topic, but basically the summary is the standard libraries typically don't support it because of ABI. So especially on the 2 platforms that we really care about for like modern phones and computers, PCs, 64 Intel and 64 ARM, neither GCC nor Microsoft stood atomic emits that instruction. Both of them report is log3 equals false for a double width atomic. And that has to do, in the Microsoft case, with ABI, because they would have to break ABI for stood atomic to support this. So actually, it's funny, stood atomic ref supports it because that's a new thing, but stood atomic doesn't because it's been there since C++ 11, and it would be an ABI break to support this. So it's not log3. And then on GCC, it goes into libatomic calls, and you have no idea if it's log3 or not. There's no way to check, like, there's no way to find out. Like, if I did this on the laptops that I had at home, and they were all reporting that is log3 equals false with GCC. And I suppose it's because they want to support these old CPUs. I don't know. Maybe somebody can tell me. But fact is, you just don't have that. So what can you do? Well, you can implement your own stood atomic, or you can maybe use boost atomic. So you can basically force that instruction being there, but that is a lot of work. Or you just don't use double width compare and swap. And is this something that we can even do? Like, we just saw that we kind of need at least like the pointer to the control block, and then the ref count, and the what was the other thing? The alias pointer index or something, or the pointer difference. So we cannot cram all of this into one word. Well, there is a technique called pack pointer, and that is used both the Vladislav's implementation and the Folly implementation. It only works on 64-bit, but what we're doing there is we're exploiting the fact that 64-bit Intel actually doesn't use all the 64 bits for the address. It only uses 48 bits. Right, so Intel machines have a 48-bit address space. They now introduced 5-level paging, which I think uses 57 bits, but that's only on special hardware. I think there is now a Linux kernel supporting it, but in any case, it's like an opt-in thing because, surprise, surprise, Hiram's law, there is lots of software out in the world that depends on those 16 bits being unused. So you break all of them if you make it the default. So using the bigger address space is an opt-in kind of thing. So I think we're good for at least another decade with this strategy. So we can use the 16 bits here in the front, and we can also use the 3 or 4, depending on what max aligned he is. Alignment bits. And on ARM, it's pretty much the same story. There is a 39-bit or 48-bit address space, and the other bits you can just use. They are also introducing a bigger address space, but again, this is opt-in only. So what we can do is we can now basically cram the pointer to the control block and the local ref count, like pointer and count. We can cram them into one integer. And so the 16 bits are the ref count, and then the rest is the address. And then we need to basically shift and mask depending on which one we're going to get out of the integer. And then if you want to set it, you need to do the same bit operations in reverse. And then we still have, so we have now this value, and that's the kind of one integer with the control block pointer and the ref count, right? And we're doing this kind of pointer packing approach. We still have this problem that we need to store the alias pointer. So Folly's solution for this is, I should say, Anthony Williams uses double with compare and swap. So if you don't, and he uses std as well. So you have to be like on macOS, or you have to be on some kind of environment where std double with says is log3 equals true. So that's not the case on Windows. That's not the case on GCC by default. But on these other two implementations, they use pointer packing. So what Folly does for the alias pointer is that they basically wrap that into another, there's another level of indirection. So they wrap that into a separate object, which in their case is just another shared pointer. And then basically they have this extra indirection. The problem is that in order to allocate this additional wrapper object when you want to store an alias pointer, that's again a memory allocation. So that's again not log-free. So we can again not do this. So what I suggest is that we can again now move the allocation from atomic shared pointer to the constructor of the normal shared pointer. So we don't have the allocation on the atomics. The problem is now it's overhead for every alias shared pointer. So our atomic operations are log-free, but the kind of naked shared pointer, whenever you create an alias shared pointer, you get an extra memory allocation there. And now we can't get around it because we only have one with compare and swap. We don't have any more space to store this alias pointer anywhere else. So we have to pay for this overhead. So we can't really use a std shared pointer anymore, right? Because if you have std shared pointer, like it's not acceptable to pay for this additional allocation every time you create an alias shared pointer, right? It's what you don't pay for what you don't use. So you need at this point then a custom shared pointer that has this additional overhead, and that's the thing you're going to use with the atomic. So here's kind of just an overview over the existing 3 open source implementations. Portability, Anthony Williams is not portable. It requires double compare and swap. And again, we have this table here. So it only really works on Mac or on Clang. You can compile with this flag, but then you need to make sure that everything is compiled with this flag. If you're on Linux, Clang, that's kind of the exclamation mark there. You need to make sure that everything is compiled with this flag. Otherwise, you have 2 different implementations of std atomic in the same binary, which means ODR violations, and you don't want to do that. So you cannot normally do this on either Linux or Windows. So the Anthony Williams version is not portable. Vladislav's version works anywhere where you can use this pointer packing trick. So that's good. Folly It's also not portable because it actually requires the GCC standard library, because they are using std shared pointer directly. So the other two, they have their own shared pointer. Folly hooks into std shared pointer, and they have this evil trick where you use explicit templates associations to get into the private members of a class. Has anybody seen this trick? And they do that with std shared pointer to get to the ref count, which is horrible. And they only done it for GCC. So they say, well, we accept pull requests for the other two standard libraries if anybody wants to do this, but yeah, anyway, it's not portable. None of them support lock-free alias. None of them are actually lock this alias shared pointer case. Anthony's one is mostly standard conforming. He implemented pretty much the whole interface as it is in the standard. There's just a very few small things missing. Vladislav is not complete at all. It's only a very partial implementation. It's missing exchange. It's missing a bunch of constructors. It actually completely, so the second implementation here, he actually doesn't do anything about the alias pointer case at all. Like if you try to create a shared pointer to base and give it a pointer to derived, it just crashes. And then Folly is actually relatively complete. Like it doesn't support weak pointer, but the API of shared pointer is mostly there. And then the last row here is whether it's production ready. And then Anthony Williams's is just a proof of concept. He has a commercial version which is closed source, which I've never seen because it costs money. Then the second one is also just a proof of concept. It's within 5 minutes I got it to like both of them within 5 minutes I got them to crash because something wasn't supported. Folly is the only one that's actually both free and open source and used in production. Okay, so now I have 3 minutes left, so I'm just going to very, very quickly whiz through some benchmarks I did with these three. So this is a very crude benchmark, and I'm pretty sure I'm not doing this correctly. And if any one of you has experience with how to benchmark this kind of stuff properly, please talk to me because I want to know. So I did this like really crude thing where I just have a bunch of threads and from 0 to n or something that are just hammering this atomic shared pointer in a cast loop. And then I have one thread where I benchmark how long does a load take, how long does a store take, while the other threads are hammering it. And then the amount of other threads is basically the variable. So I'm kind of measuring kind of the normal contention on an atomic at the same time as I'm measuring the actual performance of the load or the store or whatever. So it's not a good way to do this. I know I just can't come up with anything better because I don't have much experience with benchmarking lock-free things like that. So maybe somebody knows something. Please talk to me. But anyway, this is the result. It kind of looks as we expect. So there's two compilers where I can compare multiple implementations against each other. So here is, I compared the libc++ on Apple Clang, which uses locks inside. So they only have the freestanding functions, actually, so I wrote a little wrapper around that. And then Anthony Williams and Vladislav. And you can see, first of all, the behavior that we expect is that the lock-free, so the second and third are the lock-free ones, right? That the lock-free ones, on average, are much slower, which is exactly what we expect, but that the worst case is much better. So the worst case, if we get to more threads for the mutex version, goes through the roof, because you might just be waiting on the mutex for a very, very long time. And for the lock-free ones, the worst case is several orders of magnitudes better. And that's exactly why we want to use lock-free structures or lock-free types, because we care about the worst case if we're in a low latency environment. We don't care about the average case because we're on a tight deadline. And then we also see that Anthony Williams is about 2 to 3 times slower because it uses double width compare and swap, and Vladislav uses single compare and swap and pointer packing. So that's the load. I also benchmarked like store, compare exchange 1, and then compare exchange in the loop. The store, Vladislav has a weird store implementation, which is quite inefficient, but then his compare exchange is fine. It looks pretty much very similar to the load. But then if you do compare exchange in the loop, it gets very slow, and there it's actually not better really than the mutex versions. Because what you're doing is one compare exchange, that's already a cast loop, and then you put the whole thing into a cast loop. So you have like a nested cast loop, so that's going to be super expensive. So you should not do that with a log-free atomic share pointer. And the other compiler where I can compare things is GCC, because Folly compiles on GCC. Anthony Williams doesn't, but Vladislav does. So I can compare those two against each other and again against the standard version. And it looks pretty much the same. And interestingly, like Folly and Vladislav, they are very similar. Like if you look at the load, so this like reference, what was it, batching, should be, I was expecting the Folly version to perform a lot better here because of the reference counter batching, but like it doesn't, or it's not measurable. Maybe I've benchmarked it wrong. Yeah, so these are kind of the benchmarks on these 3 existing implementations. What I want to do is I want to do better benchmarks, and obviously what I want to do is I want to implement my own. So because now, yes, just 1 second. So because now I know how to make the earliest case log-free. So I'm obviously implementing my own version of this. Unfortunately, it's not ready yet, so I can't show it to you today. And kind of this is where I want to be in the end. I want to have a portable implementation where you can choose if you're doing W compare and swap or the pointer packing. I want to implement the log-free earliest pointers, as I explained. I want it to be standard performing, and hopefully somebody will one day find it useful. Unfortunately, that implementation is not ready yet. But yeah, hopefully I will be able to release it very soon. And that's it. Thanks.